I hope that, yes, thank you. Mike has turned on the recorder. If you do have any questions, enter them into chat and we'll deal with the questions at the end. So, Len, over to you. Thank you.
Thanks, Frank. Hello, everyone. My name is Len Barry, a member of the CMOS Ottawa Centre Executive, and it's my pleasure to introduce David Parsons today. Since David has a lot to tell us, I'm going to keep it brief. But let's start back in 1982, where he got his PhD in atmospheric science at the University of Washington in Seattle. And very quickly, he transformed or translated his work into NCAR, where he was a scientist there from around 1984 to right up to 2010, where he ended up, 2008, where he was a senior scientist at the end at NCAR in Boulder, and including many prestigious functions like Deputy Director of NCAR Earth Observing Lab, Director of 2 interagency project offices, and a manager of a research technology facility. I had the pleasure of getting to know David in the World Meteorological Organization in Geneva, where he came and joined us in the implementation of the World Weather Research Program, heading up as a chief of the research division. And he was there until 2010. Then he transitioned to a professor position in 2010 to the University of Oklahoma, where he's been until 2024, and now is transitioning to his old stomping ground in Boulder with another research group. So, and that's he joined Northwest Research Associates in Boulder doing that. So, David, without further ado, I would like to turn the floor over to you.
Thank you, Len. And Len was my boss at the WMO, so it's a pleasure being here. And I just want to say about the School of Meteorology, we became #1 in atmospheric science funding, finally passing University of Washington and Colorado State in federal funding. But this talk is interesting. It comes about from Jason Chiappa, who's a master's student, and he was taking a class in seasonal variations and research associated with that. And he developed this project. And Jason is, for master's students, got a number of journal articles, conference presentation, was the National Weather Service or the National Weather Forecasting champion. And he's actually just left the University of Washington, and he's now job hunting. So there's his email if you are hiring. So a little bit about extreme rainfall, going way back to Kevin Trenberth's work when we were at NCAR and they were bringing weather and climate folks together. It was expected, the study said there should be an increase in extreme rainfall due to increases in humidity in our warming climate, and extreme rainfall has increased at a number of locations around the world. And oftentimes the longer duration events tend to be consistent with the increase in atmospheric water vapor, but the subdaily extremes are growing at a much higher than expected rates at many locations. There's a list just of a subset of publications, and there's a picture also of a flash flood in Davis, Oklahoma, from the remnants of Tropical Storm Bill. There was thousands of children at a campground, but fortunately no one was injured, but it was a lot of rain. And just to say that the accurate prediction really matters. Work at the World Bank suggests that about 1.5 billion people are in substantial risk from a 100-year flood. Part of this is urbanization, moving to coastlines, et cetera. And it's the deadliest storm-related phenomena in the US over the last several decades. And predicting this location, magnitude of these events is critical for public safety, not only, but also environmental impacts, health, and the economy. And there's a picture from one of the cases I'll talk about later, 17 inches of rain in less than 24 hours, number of fatalities. So the first question we'll look at, what are the characteristics and trends of these extreme rainfall events, EREs, over the central and US? And we used a high resolution data set. And a lot of the results here are taken from a GRL paper that Jason Chiappa led, and there's the co-author list. So the one thing that's different about this is that we were using hourly stage 4 data from NSEP, and this is on a 4-kilometer grid. And this is important because of the structure we'll talk about later in the talk about these extreme rainfall events. And we're begin by just looking at the 12-hour accumulations, if they're more than the 10-year recurrence interval. But we actually are also looking at 50, 100, 500,000 year events also. I'll just hint at later in the talk. And we were grouping these points of exceedance together within 12 hours, but how it varies over there within 250-kilometer points. And this is really, there's a couple articles in the literature that talk about this, defines a mesoscale system. Jason Hand QC'd it, but then also developed automated techniques. And we'll talk more about MCSs, but other categories will be mentioned. And there's the 3 statistical tests. I won't really go into it too much here, but the Mann-Kendall, the Kendall-Tau, and the Thielsen slope that were done on that. And then this is just a little bit of a background, what the thresholds are for the 10-year intervals. You can see that over the Gulf Coast, it's very high. There's also a higher area over the eastern plains along the coast. And then this is just a picture of what the summer events of exceedance looks like. And you can see a lot of small points, but then you have these very, very large elongated tracks. And this is just the seasonal. You could see December, January, February, not many of these tracks. And this is the overall accumulation. You could see the darkened March, April, May, starting to get tracks sort of north of the long coast up and through the Great Plains. And then June, July, August, large number up in this area. And then in the September, October, November, you still get a lot of these tracks. And you could see that these tracks are really often the ones with really challenge to need to get this right because of the impacts on society. And we also looked at the extreme rainfall by season, and including the gray, this is all of the events. And then the black is removing the tropical cyclones and the isolated convection out. And you could see that it really tends to be much higher in the summer, increases in the spring. Fall also has a number of events. And so you're really looking at summer is the time where you have much more of these. And then just looking at the diurnal variation, this is isolated convection. You can see isolated convection, the event count is pretty similar to the mesoscale type systems, but then there's a rapid fall off, and this is in UTC. So a rapid fall off into the evening, the night, into the early mornings, where the MCSs have a much weaker decrease in the event count. So this sort of says, well, getting the mesoscale right really matters around the diurnal cycle. And then just looked at, this is the Mann-Kendall test, the summer increases that all these different tests are in the journal article, but you could see that really the summer shows an increasing trend over this 21-year period. And so this is the non-filtered, and then the filtered, removing those errors, you have this very significant trend. So can't say climate change because it's only a little over a 20-year period, but there is this increase. But then if you look at the count, you can see there's quite a big variation in the count, but they're increasing by about 17% per decade. And and it's statistically significant. And then if you look at the actual exceedance, where you're summing these events together for the amount of rainfall, it's a much larger increase, about 30%. It's just below the confidence interval due to interannual variability, which you could see is quite large, but I haven't added it in. But when you add in 2024, this trend becomes statistically significant. So big interannual variations, but then also you have this general trend of over the last couple of decades, plus a little bit, this general increase. So, and if you actually look at the mesoscale count versus the isolated count is actually decreasing, and the mesoscale convective systems are actually increasing about 24% per decade. And this is interesting. Isolated convective storms producing extreme rainfall tends to be decreasing over the US, but the number of mesoscale convective systems are increasing. And I think I mentioned this a little bit later. There are a climate study that suggests that this is something likely to happen as you get a warmer climate with more water vapor, less radiational cooling at night near the surface. And looking at the trends over the diurnal cycle, could see near or after midnight, you have a statistically significant trend, and this is for 10, 50, and 100-year events, that there's more of these events lasting after midnight into the morning hours. So this is, again, consistent with climate change, but it's too short of a period to say it's definitely true about climate change, but it is, the Mann-Kendall trend tests say it's statistically significant. So the fact that ERAs are often nocturnal and nocturnal increasing during the night, this is consistent with the idea that flash floods with convection occur more at night, going way back to Bob Maddox's studies in the 70s. And summertime convection over the central US tends to have a nocturnal maximum, but it's actually, if you look at many, many continental locations, they tend to have this often. So extreme events are tending to be more nocturnal over continents. And for us, we found a statistically significant increase. And okay, this is just the other scientific love of my life, that the accurate prediction, nocturnal convection over land masses, is a challenge for weather models. This is out of the European Center, and climate models from Tang et al. And the thing about nocturnal convection, it's often maintained by different mechanisms in daytime convection. You think of daytime convection, you get a storm outflow, you get squall lines, but during the night, you actually get bores, you get nocturnal low-level jets, ascent downstream of elevated terrain, changes in frontal structure. And then this is just a picture from a journal article that I did a while back. And this is a vertical profile looking up. So this is a scattering layer. So you could see when a bore goes by, you're lifting this layer from 2 kilometers to up above 4 kilometers. It's an undular bore, so you're getting the undulations. Here's the strong vertical motion, weaker descent, upward, downward, upward. And so you're, strong lifting up aloft, strong lifting about a kilometer or so by this one air up at 1 kilometer. And the fact that this is a low-level jet environment, here's the winds. So oftentimes the greatest instability is up in this layer. So you're lifting this layer by about 1 kilometer. And this lifting can cover areas from, you can see the journal article here, covering areas of about greater than 10,000 kilometers squared. And unfortunately, there's some nice work by Aaron Johnson and Risto Chapilski that say to get these spores right, you need very high resolution. So this is getting nocturnal convection right. It's dynamically complex, and the modeling is more of a challenge. And for parameterization, it's a big challenge too. So that first question says that ERAs associated with MCSs are increasing with a greater trend, night to early morning hours, but the data set's non-uniform. Nocturnal convection is a major challenge, and mesoscale convective systems, extreme rainfall events are increasing, isolated convection is not, and significant interannual variabilities. But the speaking about trends, you have to be cautious because it's a 21, now 22-year period. And the big caution, and it's discussed in the GRL paper, that the stage 4 data that we used, actually, there's upgrades to radar data processing, radar processing techniques. So caution in the findings, especially for me, the isolated versus mesoscale convection, but it's consistent with other studies that looked at climate systems in different data sets. And but the river forecast centers that actually produce this data were really optimistic about the data quality not impacting the trends. And there was a strong reliance on correcting errors with rain gauge data rather than using just the radar data. So they were really, the centers we talked to were really saying you can trust the trends. But the interesting thing, this is the errors early in the system. There's a data set, there's a lot of errors. It's decreasing with time. This is the errors we detected. So you may say, you know, there's you're changing the data set with time, so you may not trust it. But then the other side of the argument is, well, when the data set was poor, we were removing a lot of errors. So it's an inconsistent data set, but the 4 kilometer will show in the talks things coming up. The 4 kilometer resolution is really, really critical to looking at these trends and structures. So the just checking the time here. The next question is, how well are we actually predicting these trends, these EREs with seasonal forecasts and weather and climate models? And this part of the talk, Jason's still involved, but we're also working with Yvonne at the European Center, and Andreas Preen, a superstar at NCAR, who done a ton of work in extreme rainfall events. Look at his Google Scholar, you'll just be so impressed. And he's recently moved to ETH Zurich to be a faculty member there. So let's look at the prediction. So from the paper in GRL, what we did, we looked at 3 high years in the period and 3 low years. And we looked at the error 5 reanalysis. And one thing we found, we looked at just a ton of different fields, but these are the fields where there was statistical significance. And here's the at the 0.5, and then the thicker line is the 0.7 correlation. And then the stippling is where the composites are statistically significant at the 90% confidence level. So you could see there's this large stippling area that says, so, okay, active summers have more total column water vapor, and this is the summer average. So suggests there may be some way to do seasonal prediction. And then looking at the vertically integrated water vapor flux, again, the 2 lines looking at the correlation, but then the stippling. So when you have these high years, you tend to have stronger transport from the essentially subtropics, even the tropics, up into the Great Plains. And you tend to have this high integrated water vapor area moving across. And this is consistent with studies, the Mo et al. Saying that more heavy rainfall, you have anomalously high moisture transport. And then people looking at individual flash floods, so list of publications there, suggests that it occurs when you have this higher water vapor transport. So more column water, more water vapor transport. And then here's the surprise. The statistically significant deepening is this extension of the high pressure, but it's up at 500 millibars. So initially you may see, oh, the North Atlantic high, Bermuda high is different in these high years, but actually the that's above the Bermuda high, the way you normally look at what people talk about in the literature. It's a lower high pressure system. So whether this is a ridging on the East Coast, bringing in more water vapor transport, cooler temperatures, and optic forcing, this is something to we're looking at now to try to understand why, looking at shorter time scales. But these results all suggest a path for seasonal prediction of summer with more extreme rainfall events. So seasonal forecasts based on the positioning of the flow, water vapor, geopotential height pattern at 500 millibars, we may get some skill in predicting seasonal type findings. So what about shorter time scales? Well, this is just the picture that these banded extreme rainfall events, they're so narrow. So you can imagine this narrowness, 20 kilometer, 30 kilometer wide, is a real challenge for global weather and climate models. So we'll look a little bit at the modeling, and we're currently using looking at the prediction of numerous banded events using high resolution regional forecasts, a statistical approach using the ECMWF ensemble, and we're also starting to look at operational predictions with global models. And we're also looking at the most extreme events, so 100 to 1,000 year. So just what these events look like using this stage 4 radar data. I'll just show a few cases. So here's the stage 4 data. So 11.41 inches of rain was the max. You can see there's just these narrow bands with kind of localized heavy rainfall. So narrow bands, and this was part of $1 billion disaster. So you could see, again, this is going to be a challenge for coarse grid models. Another case, hundreds without power, and again, another 10-inch type event, another sort of very, very narrow band within this broad precipitation area. And another event, severe storm flash flooding event, 7 inches across Indiana, again, fairly narrow, another sort of localized event here, but it's occurring in this broad area of precipitation. And then Kentucky flash flood, 15 were killed. It also hit St. Louis, and one person died there. And you could see this sort of very, very narrow, almost two multiple bands. And then here's that heavy rainfall, and we're, again, up around 10 inches or so. And just looking for that last case at the synoptic surface maps, it was a nighttime event, and it's just north of a stationary front. So this almost goes back to the old ideas from Bob Maddox in the 70s that these extreme events are often nighttime north of stationary fronts. And good. So this is the reflectivity, and the arrows and dots show where that narrow band of heavy rainfall is. And you can see it's just, numerous multiple cells moving by within a broad area of significant rain. So you can imagine that if you're, have a global model with parameterized convection, getting this band of strong cells moving past one location within a larger scale of heavy rainfall, it's going to be, a really big challenge. And again, it's north of the stationary front. And then I'm showing optimistic findings today. So I've actually picked out a case where the models did quite well, but that's not so uniform. So this is what the 24-hour ensemble mean for NOAA did. So it's getting the band in a pretty good location. The rainfall's down around 3 inches or so. So it's under predicting the rainfall amount, and that tends to be pretty common. As you go 48-hour forecast, this is another common thing that happens with these events. If you keep predicting them, the rainfall amount drops and they move to the north of this front. So this is 48 hours. It's saying, okay, 1 or 2 inches here, which is different than the 7, 8 inches of rainfall that you actually observe. And then 36 hours, it's again showing, under an inch or two, but the structure is pretty well. And then the 48-hour ensemble mean is actually getting up at 3 or 4 inches. So depending what time you look at and, what fields you look at, you come up with different results. So convective permitting models appear to have some success in this short range prediction. And I showed a very, very successful event. There's some events that they completely miss, a smaller number of events. And the errors seem to be associated with smaller northward displacement, but also an underprediction of the rainfall. So what about global models at longer time scales? First thing we did, we looked at the reanalysis. So here's a 500-year Tennessee flood with the observed rainfall data. Here's the reanalysis. I think it's pretty safe to say that the amount of rainfall is greatly underpredicted, but you're not getting this structure of the extreme events at all. So, we use the Error 5 reanalysis to look at the flow regimes, but to look at the extreme rainfall events, and you would expect that with the resolution of the European Center model, it really doesn't do very well. And Yvonne has been looking at the statistical processing of the ensembles, and this is that event. This is what they were predicting. So this is extreme forecast indice. Does pretty well in terms of getting that band right. And then 12 to 36 hours, 24 to 48, northward movement, 36 to 60 hour forecast. Now it's still getting an extreme event. 48 to 72, the location's off. But they're still predicting that. And then 72 to 96, it gets the location about right, but the belief in the ensemble is pretty small. 84 to 108, it's out over here. So questions to be addressed. The skill in how well do models do the skill in prediction EREs is a challenge. Is it a challenge? Seasonal forecasts tend to do well for high and low years, but this was essentially looking at the reanalysis. So looking at real seasonal forecasts may be possible, and we're starting to look at this now, and also try to address the question, what's going on at 500 millibars along the East Coast that suggests that that's true? Is it some deepening of the subtropical high, eastward extension, etc.? So convective permitting models appear to have some success in short-range prediction of extreme banded events north of stationary fronts. We're looking now, I didn't show it because it's something we're just producing in the last couple of weeks, but we're looking at 100-year events, 500, 1,000-year events, and the convective permitting models seem to have even less success in getting those more extreme events. The reanalysis tends to have problems, likely due to the resolution being up over 30 kilometers or so. And the updated statistical EFI appears to do well in predicting some events, but there are events that seem to be completely missed. And we're suspecting that these 500,000-year events tend to be more localized and are going to be more of a challenge to get. And then there's both the even when the models do well, the convective permitting models and the European Center EFI tends to have small errors in location. And the most extreme events, the ones we're looking at now, are smaller scale and even more of a prediction challenge. And so what are the characteristics? EREs are increasing. The largest events are accumulation events, tend to be relatively narrow bands. The interesting issue is also just the interannual variation in these events, and getting the skill in seasonal predictions is important for this. And our study suggests that there may be some seasonal challenge, but seasonal prediction skill, but we were looking at the actual flow patterns rather than the seasonal prediction of those flow patterns. And there's some skill in convective permitting and statistical, although the I've showed an optimistic case. I should have shown a terrible case, but it's a nice day to be talking to colleagues. So there are cases where it's doing very, very poorly. And then is there does this have other implications for global modeling? And it's something that we're working on, but for the 30-minute talk, I haven't shown that there's a challenge in representing multiple mesoscale convective systems. And this is this Carbone effect that Rit talked about several years ago, that you tend to get a cluster of mesoscale convective systems that move east from the across the Great Plains. And when you use systems with convective parameterization, you don't get the movement of the individual systems right for the European center. When you turn off the parameterization, you tend to get the movement better, but you don't get this downstream development that impacts the Rossby waves and can actually cause Rossby wave breaks and blocking over the North Atlantic. So thank you so much for your invitation, and thank you for your time. And it was kind of a short talk, but I was told about 30 minutes. So I'm happy to go to questions now.
Well, thank you very much, David. So far, you have given us so much information that nobody's written anything in the chat.
Uh-oh.
However, what I'm going to do, therefore, is just let people ask through video, and we have Peter raising his hand. Please go ahead, Peter. And anybody else that wants to question, just raise your hand.
Thank you for that presentation. That was great. I have a couple of questions. One basically is the linkage with respect to lightning. I'm wondering if you've studied that at all. And the context is because we've had the same claim about EREs increasing in Canada, but if you look at the lightning statistics, which go back 20 years, or 22 years, the lightning actually is not increasing at all, and it's actually going slightly down. So I'm wondering if you looked into that at all. And then the next one is related to the IDF curves that you mentioned, the 50-year, 500 to 1,000-year events, which comes from the IDF curves. I'm sure you understand. And my question with that is, it gives the perception that these things occur every 500 to 1,000 years, but I think these are IDF curves generated at a point. So it's kind of like lightning. If you have your house hit by lightning, it's going to happen once every 500 to 1,000 years, but over an area, much more common. So I'm wondering if you've done any aerial studies of the frequency, which would kind of put it into a different kind of context.
Well, thanks. Those are great questions. The lightning, I wonder if that has some connection with the fact that the strong isolated systems are decreasing while the mesoscale systems are going up. And this is not my area of research expertise, but just living in Oklahoma and Colorado, it seems that the lightning, especially the cloud to ground, tends to be much more for isolated strong systems. And then these mesoscale systems, there's a lot of lightning, but perhaps not as much. So I guess I'm just showing my ignorance on that point. I don't know, do you have any thoughts on that?
Well, I've looked into the prairies in Canada. Would probably be representative of the Midwest in the United States, and the precipitation is very skewed. I mean, total precipitation in the prairies in continental climate is heavily skewed into the summertime, so convective events.
Mm-hmm.
So if you look at the the total precipitation of Winnipeg, for example, or North Dakota, somewhere, places like that, the vast majority of precipitation on an annual basis occurs in the summertime due to convective events. And if you look at any average convective event that hits Winnipeg or Fargo, North Dakota in the summertime, all those that produce a lot of rainfall also produce lightning. The odds of getting one without the other are pretty slim. So you'd expect on an annual basis, if you had more precipitation, you'd also get more lightning, because the two usually go together.
Mm-hmm. Yeah, and it's interesting. isolated versus the larger extreme events. I didn't include the 2024 because it's something we're working on now, but the isolated events are, really, really low, and the mesoscale events are really high. And it'd be interesting to look at these different years, to look at the lightning data across the U.S. to see if there's interannual and trends with that, just to try to link the two.
Yeah, that'd be great. And do you have any thoughts about the other question I had about the IDF curves and the 500 to 1,000 year events?
So in terms of the location, and this is maybe more for we have large differences in the locations that vary from year to year. And initially, when you look at the whole, the whole system east of the Rockies, you tend to come up with areas where there's been more rainfall. But if you add another year or divide it into sub years, that the locations just seem to vary tremendously. In this past summer, the events had all moved to a peak near the East Coast, which is something we haven't seen before. So I think that to look into the areas and how in depth at the variation in the trends, I think it's something that we really need a longer time range than we have. I'm not sure if that's answered the question or not, but
Probably time to move on to someone else's question.
All right. David Grimes.
Thank you.
David?
yes.
Where did you go?
Okay,
Go ahead.
so how are you, David? Thank you
Good.
very much for doing this. It's been a great talk.
Thank you.
I was focused on the modeling side, and I was wondering, with the I'm wondering if the approach to get down to the small scales wouldn't be a good application for AI type of modeling. There's been that, an increasing trend towards using AI for, in the case of producing ensembles, for instance. I mean, there's this movement, and I just wonder if you had any thoughts on the applicability of that, because these are kind of small scale events that, if you were teaching an event for what it needed to look for, whether it would be applicable operating really within the context of say a regional model or a small grid model that, could be the sort of driving, the drivers for improving that kind of predictable outcome. Anyways, just the thought. I was looking, it struck me when you were showing the ECMWF data. It gets the band right, but it doesn't actually, get the intensity at all. And so I was just curious what your thoughts would be on that.
Oh, that's a great question, and thank you. Right now we're working on a National Science Foundation proposal to use AI on these data sets, and to do the European Center, and then use the smaller scale models for that. And there's colleagues will collaborate with Russ Schumacher at Colorado State is using a type of AI. It's a good type, but maybe a little dated. And then Amy McGovern, who's one of the weather AI leaders, has also done just got a proposal funded on AI in extreme. So I think we're going to collaborate with them, and because of the collaboration and what they're doing, we might be winding up using the global models more than the regional, but depends on what they do. So I think this is a really good point, and hopefully we'll be funded to do that. And we were encouraged to by NSF program manager that we work with to add AI to our grant and do that. So we'll just see how it goes. And it's interesting too, the European Center, maybe a few weeks, a couple months ago now, you can download the software that the European Center has developed, and also that the private sector companies that are using their data and putting AI forecasts online wind up doing. And one thing I do tend to wonder about is that the AI for the global models sometimes tend to produce almost too smooth a type of flow pattern. So it'll be interesting to see if the high resolution models tend to do much better. And I think that we're thinking of it may be a little outdated, but using the convolution neural networks and heat maps to try to come up with reasoning as to why the AIs do occur. And the heat maps are, to me, really interesting because looking at forecast busts, it was sometimes things you wouldn't expect that were showing up as increasing the likelihood of a forecast bust. So work's kind of starting in this area by others, and we're trying to move into that area ourselves. So great question.
Yeah. David, any more?
And I think the higher
Sorry, I
resolution.
was on mute. I just wanted just a quick follow-up. It just struck me, you know, what in the earlier slides where you were showing the distribution of these significant events, where you get them along the coast along the East Coast, and then you've got that sort of pillar that goes up into the Eastern Great Plains. Just made me think that it's difficult to understand sort of the boundary layer physics that are probably having some influence on those kind of behaviors in those particular regions, and AI might actually provide a sort of an interesting insight into as a teaching method that could then be applied. So I look forward to your work in that area coming up. So thanks very much.
And just as long as you brought up the boundary layer too, that you often have that stable boundary layer in this jet overrunning, but when the jet gets strong and you have more water vapor, you tend to get rid of the stable layer at night. But then these extreme events happen when there's a front there. So we have this, air being lifted above the nocturnal boundary layer. So that's kind of an important challenge for numerical models. And if AI can help, that's a good path.
Yeah.
Right.
Excellent. Thanks a lot.
Len, you have your hand up.
David, I had a specific question regarding your trends in counts and exceedances in that slide. There was a minimum in 2012 that was that had some autocorrelation in it in the count, and I wondered if you'd thought about what might cause that. What would cause that minimum? Would it be related to any large scale circulation features that you might factor out and then give you better explanation of trends in the actual convection? Like, is there an El Nino or La Nina effect there, or in the say that count, MCS count, for instance?
Yeah, it's interesting because this was the MCS count. I think this was one of the low years that we've used, and so there are significance in the large scale flow pattern, and then it's a kind of a short period, but we wound up looking at a lot of the climate indices, ENSO, et cetera, to see if we could come up with any skill, and it seems we couldn't. So, trying to understand this, and with seasonal prediction, is it going to be the monthly averages of a model, or is it going to be the these larger scale variations? And So there's colleagues at here at Oklahoma that are actually, sort of going down that ENSO path with these extreme rainfall events. But for us, we didn't find any correlation, but maybe it's too short a time period, or maybe it's the occurrence of multiple variants that tend to do that. So that was something we looked at, and we wound up just not including it because we didn't really come up with any trends. So, that count from well below 100, and then a few years later, you're pushing towards up towards 180, something like that. It's and then 2024 is also up near that high area also. So we haven't been able to, we said, oh, there's these trends looking at reanalysis, but to understand how the variations besides the summer average cause these things, looking at weekly and monthly. That's another thing that the current proposal we're submitting will deal with. Okay. But yeah, we thought, oh, this is going to be great. We can, look at, the different variations and come up with a explanation, but no, we didn't.
Frank, how were we doing on the chat?
There we go. Nothing on chat. We've silenced everybody on chat. A couple of general questions while you're thinking of more serious ones. One is whether the insurance industry has shown interest in your distributions, and the other is whether the building code people are showing interest in these and adapting both of the prediction for actuarial predictions for insurance and for building codes.
For the insurance, and it's not so much connected to this work, but with extreme rainfall increasing and tropical cyclones also, that this is kind of a big issue, as you're probably more aware than I am, for the insurance industry and for reinsurance, just the amount of damage that can occur. When I gave the talk at the European Center, somebody from the reinsurance side there showed up and was, but I haven't heard much from the US on this, but we've had grad students now that have been hired into that enterprise, and another one whose dad is high up for an insurance company I won't name, that actually, is they're starting to hire more atmospheric scientists to look at the trend, and they're so localized that it's, I think that one of the bigger issues for this is really the movement of people around the world to coastal areas, urban cities. The growth is, you look at, say, Southeast Asia, so that just the heat is often a factor, but just the extreme rainfall, it's a really important thing for society to be thinking about in the future. And I think it really pushes the idea, and Singapore has thought a lot about this, the researchers and the equivalent of the weather service down there, that you really need, it's good to have high resolution models that can predict these heavy rainfall areas, because you can have millions of people living in a relatively small coastal area, often with a river coming through. So it's a important problem for society. And I think the Singapore actually did a lot of training of their high resolution models and their ensembles to get the physics right and to go forward. So yeah, it's an interesting, important problem.
Michael, it looks as if you've just joined us. Do you have a question on your mind? which case, if we've dried up all the questions, if that's the right term to use, I'm going to ask Len to draw this to a close, if you could, Len, please.
Well, David, we were very fortunate to get you on your transition from Oklahoma to Boulder to give us this presentation. We, judging from the participation, which is very strong here, we're very pleased on behalf of the membership of CMOS and the overall audience. I'd like to thank you for a very interesting and insightful talk.
Well,
So
thank you very
thanks.
much for having
Thank you
me.
very much.
Thank you very much for having me here. And I probably should have shown more of the recent slides and shown a forecast failure or two, because sometimes it's kind of a rare event in the European Center EFI to get it right. So, or not that rare, but so thank you very much. And I maybe should have shown some more things today, but trying to keep it to a half hour. So thanks.
Okay, well, thank you. And we'll turn the recorder off. And if you wanted to show another slide, you're welcome to do so.
No, it's okay.